Welcome to Pharmaceutical Calculations, a conceptual approach, lesson 22, part 3. Today we're going to take a closer look of the osmotic pressure. Now, so far we are familiar with an equation that can be used to calculate the osmotic pressure of a solution. We are not familiar though with any method that can calculate osmotic pressure differences between two solutions, let's say across the two sides of a membrane. Now, such a method would be very useful because, as we know, body fluids are never pure water, right? We are familiar with intracellular and extracellular fluids that they always contain some solutes. Such an equation also will help us determine the direction of flow of water inside the cell or outside of the cell, help us figure out whether a cell will experience expansion or shrinkage because of osmosis, and it can also be used to calculate or to adjust the tonicity of hypotonic drug solutions. Now, we are familiar with the sodium chloride equivalent method. So hypotonic drug solutions, it's not pure water, right? And we have been using the E value to adjust the tonicity to isotonic values. Such an equation may be used to also adjust the tonicity of hypotonic drug solutions to isotonic. So this is the Van Hoff equation that we have been using to calculate the osmotic pressure of solutions. We need an equation that can calculate osmotic pressure difference between two solutions. So let us derive such an equation using the same experiment as we have described before to when we have defined osmosis. The difference here is that the compartment to the right side of the membrane, it doesn't contain pure water anymore. It contains a solution. And as you can see here from the filled circles, the solution to the right is more dilute than the solution to the left, right? Now, that implies that the water activity in the right compartment is higher than the water activity proportionally, right, compared to solutes, than the water activity in the more concentrated solutions. And therefore, according to the principle of diffusion, since the semi-permeable membrane is only permeable to water molecules, water will flow from right to left, from high water concentration to low water concentration. And it will stop when the hydrostatic pressure reaches a certain magnitude, which is called osmotic pressure at equilibrium, right? This hydrostatic pressure opposes the flow of water from right to left. So now we have a method to modify the Van Hoff equation. Essentially, we're going to solve the Van Hoff equation twice, one for C1 and one for C2, and take the difference. So this is what I mean over here. So pi is equal to ICRT, okay? And now that I have two solutions, delta pi is going to be equal to I1 times C1, I2 times C2, and this I1 and I2 is the Van Hoff dissociation factors for the two solutions, especially if I use two different salts, right, times RT. Let us apply this equation. So we're going to use example 8.4 to apply our new equation there to determine delta pi. So here we have two aqueous solutions. They are both sodium chloride solutions. The density of each one is the same, although they have very different concentration. It appears that it doesn't make a difference, a little bit of solute more here. So here the first concentration is 154 millimolar, whereas the second solution is 15.4 millimolar. However, the density of them are similar, okay? And we are also given the molecular weight of sodium chloride and of water. That's 58 and 18 grams per mole. Now, our main goal here is to calculate the osmotic pressure difference of the system, okay? And based on this, actually, we should be able to calculate or to determine at the same time, by the sign of this delta pi, the direction of water flow. So we don't even need this one, but we are going to carry out also the determination of water concentration on each side of the membrane to make sure that our result of delta pi agrees with the principle of diffusion. So water should diffuse from high water concentration to low water concentration. So let us start from A. So here I call the 154 millimolar sodium chloride concentration as C2, and I multiply by the molecular weight to determine the mass of sodium chloride in 1 liter of solution. Then I apply the density of solution, since this is the density of solution, not the density of sodium chloride, not the density of the water. I apply this density to the denominator, which is 1,000 ml of solution, and I end up with 9 grams of sodium chloride in 1,050 grams of solution. So the mass of water in grams can be calculated after subtracting 9 grams out of the mass of solution, and therefore I have 1,041 grams of water. Divide by the molecular weight, and I end up with 57.83 molar of water. Okay, now I do the same, I follow the same process. So now I have 115.4 millimolar sodium chloride. I have to go one slide back. So I'm here. To calculate the mass of sodium chloride, I multiply by the molecular weight, and I end up with 0.9 grams per liter of sodium chloride. And now I apply the density of solution in the denominator again, and I end up with 0.9 grams of sodium chloride per 1,050 grams of solution. Subtracting this amount from the grams of solution, I end up with a mass of water 1,049.1 divided by the molecular weight, and you have 58.23, which is higher than, what was that, 57.83, okay? So the water activity of the more dilute solution is high. Therefore, water will flow from the 15.4 millimolar sodium chloride solution into the more concentrated water solution to dilute it, okay? Now, I could have applied directly the Van Hoff equation now for the delta P, and notice that I'm using the measured Van Hoff dissociation factor. As a reminder, NaCl in water will dissociate into 2 ions. So the calculated, that's a negative sign there, the calculated Van Hoff factor is 2 because I have 1 sodium and 1 chloride, but the measured one is 1.9 because they are a little bit more concentrated than ideal solutions. Subtracting the 2 concentrations, I end up with a negative 6.7 atmospheres. That indicates that water will leave the C1 side and it will go to the C2 side in accordance, in agreement with what we have determined using the water concentrations, right? So this is very, very nice. As for exercises, for practice exercises for you, I have 8.31 and 8.32. So here you are asked to determine the direction of flow. And here we have an osmosis experiment. The amount of liquid increases on the side of the membrane with the greater, remember, is it going to be solute or solvent here, okay? And a similar question over here, but now I'm changing the phrasing and I'm citing here isosmotic, hyposmotic, hyperosmotic, okay? Those are very nice for practice. And in 8.5, now I have 2 different solutions extracellularly and intracellularly, and I'm asking you to determine not only the direction of flow of water, but also to determine the cell volume at equilibrium. So not only, so you have to determine whether the cell will expand or shrink, but also determine to what extent is it going to shrink or expand. So this is very, very nice. And at this point, I would like to thank you for your attention. Until next time.